A very good afternoon to my fellow researchers. My name is Jae Kim, and I'm from UNIST, South Korea. Today, I would like to present our work, CAFO, Feature-Centric Explanation on Time Series Classification. This is the joint work with my collaborators, Dr. Seokju Han, Dr. Yoon Tae-hwang, Professor Jung Lee, and Professor Seok Lee. A few years ago, I used to work with a smart insole startup back in South Korea. This company produced a smart insole where I helped them build activity classification models. At that time, I was able to build a classification model with 95% accuracy using all the 14 sensors that was inside the smart insole. So this got me thinking, do we really need all the sensors as well? Are there specific sensors that are more helpful in classifying a particular activity? It turns out that domain experts from the smart insole company were more interested than I was. Knowing such information can reduce manufacturing costs by removing unnecessary sensors or even upgrade them for specialization. For engineers like me, knowing such information can be helpful because we can reduce the model size, data storage costs, and even obtain better model performance. Here are two lines where the blue inverse line represents the model performance for the same test set when we drop features that are not important one by one. On the contrary, the red truth line is the performance curve when we drop important features one by one. As such, we observe faster drop in accuracy for the red curved line, while the blue line seems to maintain performance. Here, we show that leaving only the most important 3 features can maintain overall model performance. But there are several difficulties in explaining and interpreting multivariate time series compared to different data modalities. Consider this image of a cat. When a model classifies this cat as a cat, we can overlay the attention map over the cat and easily see that the model is looking at the right features. But for time series, even if you highlight the important time segments, which most time series XAI methods have been focusing on, we don't truly understand what's going on. So this kind of explanation is a time-centric explanation, where you highlight important time segments for model performance. Such explanation might be helpful in certain scenarios, but there are times when we need a more global understanding of the model and the data, such as knowing which features are globally or class-wise important. And I consider this as a feature-centric explanation of multivariate time series. So throughout this presentation, here are the main questions we would like to answer. First, what is our method? Second, what are the key features to maintain overall model performance? Third, what are the relatively more important features for identifying a specific class? Fourth, how do you know and evaluate that the identified features are actually important? Fifth, what kind of data sets can we use? So to give a brief overview of our work is called CAFO, which stands for Channel Attention and Feature Orthogonalization. Briefly, we propose a depth-wise separable channel attention module to generate channel attention scores, which are later used for feature-centric explanation. We also propose a set of metrics to evaluate and identify global and class-wise feature importance. Last but not least, we also propose real-world and synthetic datasets called the witch finger and squid game. So let me explain the methodology section. Our CAFO consists of 4 parts, and we explain them in the order of how the data is processed. Given a raw MTS dataset, we first convert each time series channel into distinct images using image encoding methods like a recurrence plot. Here, we can see that there are 3 time series features which are converted to a 3-channel image, where each channel of the image now represents a single time series feature. The converted images go through our proposed depth-wise separable channel attention or DEPCA module. The depth-wise convolution operation enables the processing of each channel in a channel-wise manner, thus preserving feature-specific informations. Using DEPCA, the learned feature maps are averaged in a feature-wise manner. finally going through a sigmoid layer, where the obtained channel attention scores now represents the feature importance scores. For example, here, A3 represents the feature importance score for feature number 3. Are we done? No. We further propose to regularize the feature-wise attention scores to be orthogonal using a QR decomposition-based method. Our regularization method widens the distance between the feature distributions of the attention scores, which enables the derivation of precise feature importance ranks, which are crucial for feature importance score calculations laterwards. Lastly, the calculated attention scores are multiplied to each features of the multivariate time series and passed through vision-based models. Here, intuitively, attention scores with the 0 suppresses the whole feature, while a score with 1 maintains the feature for model training. In our paper, we have trained on various vision-based models, such as a ShuffleNet, ResNet, VIT, and MLP mixer in an end-to-end manner. The final loss function is as in equation 1. Now, I would like to introduce how the feature importance scores for each features are calculated. The first metric is the global importance, or GI scores. The GI score is a measure to quantify the global importance of each features with respect to the model performance. The GI score is computed by averaging all the attention scores. A high GI score indicates high importance for model performance, with low GI score indicating lower importance. This metric is helpful in identifying the important features for maintaining overall model performance. The second metric is the CWRI metric, which represents the class-wise relative importance scores, which quantifies each feature's class-wise importance. The score is calculated by first constructing the class attention prototype vectors, and then calculating the relative difference as shown in equation 2. For instance, as shown in this table, feature 1 might have higher relative importance in class 1, but lower importance in both classes 2 and 3. This metric is helpful for identifying the relative contributions of each features for each classes. Let me now share the results of our work. We first evaluate the GI scores using the remove and retrain method. Basically, we first calculate the GI scores and rank each features by their importance, then remove each features one by one based on their rank and evaluate their performance on the test set. In this figure, the red truth label represents removing features in the order of actual importance, and the inverse represents dropping features in the order of non-importance. As such, if you have successfully identified a feature as important, and if that feature was truly important, we should see a huge drop in model performance when we remove that feature. Here, we observe that our CAFO method better identifies the feature importance ranks, shown by the larger decrease in model performance, compared to using only cross-entropy as the baseline. We further show that our CAFO method is better performing than other XAI method in several key metrics. For instance, our CAFO in ShuffleNet results in higher ABC, DA, WDA metrics, while other baselines show small or even negative scores, which shows that the identified feature importance are not significant. We also show that the feature importance ranks found by our CAFO method is more consistent. Such consistency is important as it shows that the model is reliable. The plot here is the rank correlation plot between the different runs of each model. As such, each cell represents the Spearman correlation, which measures the correlations between the two ranks. The higher the correlation, the more red the cell is. The left figure shows that the correlations between the ranks are inconsistent between and within models when using only the cross-entropy loss, while on the right shows that our CAFO leads to more consistent feature ranks within and between models. Furthermore, we show that our method is also robust to non-essential features. In real-world datasets, we can easily observe extra sensors that are not helpful in classification. We simulated such problems by injecting pseudo-features. Here, the red bold lines are the edit pseudo-features. Our GI score shows that while the pseudo-feature had a 0.5 importance in the beginning of the training, it rapidly converges to have close to 0 importance as training progresses. Next, we have the CWRI score evaluation. So, one of the difficulties we faced during this research is the lack of public datasets with known class-wise importance. As such, we collected the witch finger and the squid game datasets with known class-wise importance. We have made both datasets publicly available. We show that our CAFO method can well identify the true class-wise relative importance. Now, we would like to wrap up our presentation by answering the questions we have posed in the beginning. To answer each question, our method was CAFO, which stands for Channel Attention and Feature Orthogonalization. We identified each feature's global and class-wise importance with the GI and CWRI metrics we have proposed. We have also shown that the found features are actually important based on several experiments. Last but not least, we have utilized both public datasets and datasets collected from us. Thank you for listening to our presentation.